Okay, so now I want to talk about this in a different way. So remember, this models the situation where you have a river flowing at a constant speed, so gamma is constant. It's important that the river is flowing at a constant speed, and you have this diffusion process that's happening as the river moves. Now, since the river is moving at a constant speed, we basically would just, it seems physically plausible that this diffusion is happening and the whole diffusion process is just moving. So it seems like if U is a solution to the diffusion equation, the t derivative of U equals the double x derivative of U, then the solution to the diffusion convection equation is just going to be that solution, but one that's being translated at gamma meters per second or whatever it is along the x-axis. Then I'm going to call it V of xt equals U of x minus gamma t. T is a solution to the t derivative of U equals the double x derivative of U minus gamma the x derivative of U. Okay, again, U is a solution to the diffusion equation. This x minus gamma t means it's just moving along the x-axis. It's moving in this direction, in the rightward direction, at gamma meters per second. Like physically, that's what, if our physical modeling situation is what I just described, then this exactly is a solution. But remember, we go from the physical modeling to the mathematical model, and then we solve the mathematical model. And so even though this kind of does represent a diffusion process moving along the river, and it gives us hope that it should therefore be a solution to this equation, we need to actually show that this is a solution to the equation. So our physical intuition says, as a hypothesis, if U satisfies the diffusion equation, then V is going to satisfy the diffusion convection equation. And now all we have to do is prove it. Now, of course, we saw this is exactly the form of what we got in the previous video, but let's assume we didn't go through the Fourier transform because that can be kind of messy or whatever reason. Let's say we want to show, we start from here. So I want to show that if U satisfies the diffusion equation, then V satisfies the convection diffusion equation. Okay, so let's do this. There's going to be a little note on notation that I want to make. Or not there. It's not that there will be. There is a little note on notation that I want to make because it's going to get a little bit confusing. And in general, this might be helpful for this class. So for the function U of xy, or let me say U of xt, for the function U of xt, if we look at the partial x derivative of xt, what we're meaning here is that we're taking the derivative in the first variable. It means we're taking the derivative in the x variable, but the x variable is the first variable. And so this, by definition, is something like the limit as h goes to 0, U of x plus h comma t minus U of xt over h. And so another notation that's sometimes helpful is U sub 1, or sorry, the partial sub 1 of xt. It means we're going to take the derivative in the first variable. And similarly, we'd have like the t derivative of U of xt means to take the derivative in the second variable. So I'm going to call this partial sub 2 of xt. It means this slot right here, this second slot right here is where we're going to do the difference quotient. So let me just write out explicitly. This is the limit as h goes to 0 of U of x t plus h minus U of xt over h. And this is going to be important in a little bit when we apply the chain rule, because it's ambiguous if we use the x and t notation. Sometimes so what I'm saying is sometimes when we use this notation, like here, when we use this notation, we mean two things. We're going to take the difference in the first variable and we're going to take the difference in the x variable. Here it's the same. Okay, sometimes sometimes by this we mean take the derivative in the first variable, even if it's not called x and even if their x appears differently. And sometimes we just mean take it in the x variable. So, okay, without further ado, let me try to explain what I mean here. So I want to do the t derivative, I want to do the t derivative of v of xt. Now here what I mean is I want to look at the, I want to do the derivative of v in the t variable. Okay, so this means like, I'm going to erase this, but this means the limit as h goes to 0 of v of x t plus h minus v of x t over h. That's what it means. Okay, so what is v though? V is equal to this. This is equal to the t derivative of u of x minus gamma t comma t. Okay, so here's where it gets tricky, because over here the t derivative meant take the derivative in the second component, meaning we're going to add plus h to here and then subtract that off. But that's not what we're doing here, because there's a t here as well. Okay, so that's why the notation, this is an example of where the notation can get a little bit ambiguous. But what we're going to do is we're going to use the multivariable chain rule. And what this tells us is going to be the derivative in this first component here. Okay, it's going to be the derivative of u in this first component. So partial 1 u of x minus gamma t times the derivative of this with respect to t, which is minus gamma, and then plus the derivative in the second slot. So this is going to be not t, 2 u of xt times the derivative of t with respect to t, which is just equal to 1. Okay, now if u satisfies the diffusion equation, another way to write the diffusion equation using this notation, the 1 and 2 notation, would be something like this. The derivative of u in the second component is equal to the double derivative of u in the first component. But here, u is equal, this is for, this should be x minus gamma t. Okay, so then what this tells us, let me try to do this one step at a time. This right here is going to be minus gamma times the derivative of u in the first component, and then it's going to be plus, okay, this is the derivative of u in the second component. It doesn't mean the second derivative of u with respect to t, it means the derivative of u in the second component. And the derivative of u in the second component is equal to the double derivative of u in the first component. Okay, so this is equal like this. Okay, now observe that if you take the derivative of v in the first component, that's the same as taking the derivative of v in the x component here, because x is in the first component. So what I'm saying is this right here, gamma times the derivative in the first component of u. When I say derivative in the first component of u, I mean we're going to be varying this part right here. The derivative in the first component of u is, this right here, the derivative in the first component of u of x minus gamma t is equal to the derivative in the first component of v, which is the x derivative of v. So this is equal to minus gamma times the x derivative of v, and then similarly this is the double x derivative of v. So this is going to be plus the double x derivative of v. Okay, and think through that last part there using this terminology. Okay, so what we've proven then is that if u is a solution to the diffusion equation, then v of xt equals u of x minus gamma t, comma t is a solution to the diffusion convection equation. Okay, and again, to prove this, we had to the notation gets the notation is ambiguous. It's good notation. Using these variables as the notation here makes sense. It just gets a little complicated when this operator here can sometimes mean take the derivative in the t variable. In other words, in the difference quotient, wherever you see a t, you're going to put t plus h. And sometimes it means you're going to look at the derivative in the second component, meaning in the difference quotient, we're just going to write t plus h there, but no over here. Okay, so just something that we have to get used to when we're dealing with multivariable calculus. The notation can get a little bit confusing. You just have to track through and make sure that we're understanding everything correctly. And sometimes introducing notation like this partial 1 and partial 2, which I hope will be helpful. And we're going to use this in the Laplace equation section when we look at proving something about the Laplace equation. Okay, or the Poisson's equation. All right, that's it for this video.